Hi, I'm Hochang Seok from Hochang University. I'm going to introduce our robust omnidirectional visual-inertial navigation system, ROVINS. Omnidirectional vision and depth sensing is strongly needed in autonomous driving and robot navigation to detect obstacles and surrounding structures. For example, when you're driving, you watch all directions, not only the front. It is also used for various AR/VR applications. For omnidirectional sensing, we have designed a novel multicamera setup which is practical that can estimate accurate omnidirectional depth and angle motion of the rig. The rig consists of only 4 cameras with ultra-wide field of view fisheye lenses which can see the scene behind the camera. We mounted them at the corners to maximize the overlapping region. Recently, many related works using our omnidirectional camera setup are introduced in robotics and computer vision communities. It includes visual odometry, stereo matching, and dense visual SLAM systems. All works show significantly improved results which overcome the conventional method. Especially VO and SLAM shows high accurate results in many challenging environments. Although ROVO has recently demonstrated superior performance and stability with the unceasing feature observation of the omnidirectional setup. However, the shortcomings of visual odometry remain. Visual sensors provide rich information of environment structures and objects in high resolution, but they are sensitive to illumination conditions, motions, and dynamic objects. In these challenging cases, the performance of pose estimation using only vision is highly degraded. Therefore, to overcome these drawbacks of vision-only system, we seamlessly integrate the inertial information into the omnidirectional visual odometry algorithm. We present a novel omnidirectional visual-inertial odometry system called ROVINS. We also propose a simple but effective IMU-aided feature tracking method. Finally, we conduct extensive experiments in extremely challenging scenarios and thoroughly evaluate our system. Here, we show the overview of our system. Given fisheye images and IMU, we first estimate hybrid projected images and pre-integrated IMU motion. Second, we track the intra-view feature using IMU-aided tracker and perform inter-view stereo matchings to find correspondences between the cameras. Finally, we initialize the system based on ROVO and estimate the poses with optimization-based omnidirectional VIO. Here, we show the Recoordinate system of our rig. We use the IMU as a body coordinate and each camera is rigidly attached to the body. Intrinsics and extrinsics between the sensors are calibrated. In this work, for more accurate intra-view tracking, we propose IMU-aided feature tracker. KLT uses an image pyramid where a course position is computed first and then the final motion is updated. Therefore, having good initial locations in a new frame is important for accurate and fast feature tracking. So, we predict initial feature locations by projecting 3D feature point to a new frame using IMU propagated pose. If the feature has not been registered to the map yet, only the rotation of the propagated IMU was considered for the prediction. This simple method can make the tracker to handle large motions. In this stage, we optimize states using visual and IMU constraints. The proposed VIO algorithm continuously estimates the body pose, velocity, and IMU biases at a frame rate, which resulted in a reliable calculation of the rig system's trajectory. Once the initialization has been completed, the current frame pose was updated with the pre-integrated IMU pose, and then the outlier features were rejected based on the tangential error of unit ray. After the outlier rejection, the state vectors of the current frame and the keyframes in the active local window were optimized in both their visual and IMU constraint. With the given body poses, extrinsic and map points, the visual constraint was calculated based on the tangential error of unit ray of the feature point. Tangential error is more accurate than reprojection error in our ultra-wide field of view setup. With the IMU readings between two consecutive keyframes, the measurements were pre-integrated to obtain the relative IMU constraint. Pre-integration error used for constraint is widely used for many modern VIO systems like VINS Mono. After building this nonlinear problem, we solve it using Zeta Solver. From now, we show the experimental results. First, we evaluate our system using the start-to-end error and compare it to the results of ROVO. We use 6 real-world datasets for this evaluation. Datasets include abruptly changing motion and multiple dynamic objects. In all datasets, ROVINS show superior accuracy and robustness even when the ROVO fails. Large-scale in-out dataset is especially challenging. It has been captured by a person walking around indoors and outdoors, including the opening of doors, illumination changes, and moving objects. We also evaluate the RMS error of ROVINS and compare it to the ROVO and ROVINS'20. To calculate RMSE, we use the motion captured mocap datasets with ground truth poses. They were captured in a poorly textured room in 3 rapidly changing motion scenarios, which are very challenging for a vision-based SLAM system. In the quantitative results, ROVINS shows over 2 times more accurate performance than ROVO and 7 times more accurate than RMSE. In qualitative comparison, both vision-based methods show bumpy trajectories, but ROVINS shows smooth trajectory regardless of the difficult camera motion. These results show that ROVINS can operate in an accurate and robust manner even in challenging situations. Additionally, we evaluate our IMU-aided feature tracking in mocap datasets. As shown in the table, our methods slightly increase the number of inliers and improve overall pose estimation accuracy. We also study about the effectiveness of our omnidirectional setup. The experiment is conducted by varying the number of used cameras. As a result, we observe that the less the number of cameras, the lower the accuracy. Therefore, it is quantitatively confirmed that the omnidirectional setup is advantageous in overall accuracy and robustness. Here we show the result of shaking handheld dataset. As you can see in the video, our method can accurately estimate the poses in very fast motion. Here we show the results of mocap oral dataset. Even in the poorly textured environment, our method can estimate accurate spinning and shaking motions. Thanks for the listening, and please follow the link for more results.